Okay, so as we've seen, it's possible to construct numerical one-step methods by applying quadrature approximations of integrals to the fundamental theorem of calculus. So at this time, it seems appropriate to review systematically how one constructs numerical quadrature rules. So perhaps the most systematic way of constructing numerical quadrature rules lies on this sort of paradigm of taking a problem which you're trying to work with, approximating it, and then sort of evaluating the exact solution of the approximate problem. So what do I mean by that? So if you're trying to compute some integral, for example, then what you can do is that you can imagine approximating that integral by replacing hypothetically that function f of x by some sort of approximation. And for many applications, that involves maybe projecting or interpolating this function f of x by, say, a polynomial or some other finite dimensional set of basis functions. So all right, so you take this original integral problem and replace it by the integral of some polynomial, and then the claim is that the exact evaluation of this is some reasonable approximation of the integral, so long as the approximation you've constructed is nice in some way, shape, or form. Okay. So let me sort of state this more explicitly, right? That numerical quadrature rules are often constructed by approximating a function okay, and then exactly integrating the approximation. Okay. All right. So let's choose a particular form of approximation. It's like in the simplest examples, which you're probably familiar with, is this idea of polynomial interpolation. Okay. So so we're going to recall this idea of polynomial interpolation. Okay. So what is that? Okay, so say you're given a function. Let's call it g. All right, and you sample g at a number of distinct points. Let's say s distinct points. Okay. So you happen to know g. It's like at the points, let's call them c sub I. Okay, and the values at those points, let's just denote by g sub I, and this is true for I equals 1 to s. Okay, so that's the data which you're given, and then without loss of generality, it's like you can order, it's like these points, c1, so that they're in increasing order. Okay, then the claim is that there exists a unique polynomial P of x, okay, which is given, which has degree up to s minus 1. So a0 plus a1x all the way up to a sub s minus 1 x to the s minus 1. Okay, such that the polynomial evaluated at the CIs recover the GIs. Okay, so the polynomial evaluated at the CIs equals to GI for I equals 1 to S. Okay, so if you think about that, there are essentially S unknowns. It's like in a polynomial of degree S minus 1, okay, which are of course just the coefficients of the monomials. And then you have n constraints, if you will, which are the function values at the points I equals 1 to S. So so it's at least conceivable that such a system, it's like, can be solved uniquely. Okay. And if this condition holds, then you say that P is an interpolating polynomial. And it's called interpolating because there's a polynomial, some continuous function, which goes through, it's like all the data points. Okay. So this is not the only type of approximations you can, right? So it's not necessarily the case that the functions you choose to approximate some given set of data, it's not necessary that it has to go through the points, but if they go through the data points, then you call them interpolating. Okay, so so that's a little bit about polynomial interpolation. So let's try to use this idea then to develop a quadrature rule. Okay. So let's consider a function g from some unit interval to the reals. Okay. And then we want to approximate this by exactly integrating the interpolating polynomial that goes through the points at what are called quadrature points. And as before, it's like, let's just order them, and they have to, again, lie in the interval from 0 to 1. So C1, C2, all the way up to CS. Okay, and the basic idea then is that, you know, it's like we have this reference interval, but once you've developed a quadrature rule for a reference interval, then you can do rescaling. It's like to develop a quadrature rule for an arbitrary interval of integration. Okay, but so for now, we're just going to work with a reference interval here. Okay, so so you're given a bunch of quadrature points, C1 to CS, all right, and you want to look at the polynomial, the interpolating polynomial, which goes through those quadrature points. So how do you go about doing this? So one way to construct an interpolating polynomial is in terms of what are called Lagrange polynomials. Okay, so I'm going to make the following claim, that the interpolating polynomial is given as follows. there's what's called the Lagrange interpolating formula. Interpolation formula. Okay, and it says that if I consider a polynomial p of x, which is some linear combination of what are called Lagrange polynomials, then this thing is going to be interpolated. Okay, so it's going to be the sum from I equals 1 to s, right, the s quadrature points, and I'm going to evaluate the function g at these quadrature points, ci, and they're going to multiply into what are called Lagrange polynomials. I'm going to denote this by L sub I of x. Okay, so these are just basically coefficients which are obtained by evaluating the function g at quadrature points, and then this thing here is a polynomial which is going to be of degree at most, well, it's going to be degree s minus 1. Okay, so let's look at what these Lagrange polynomials are. Okay, so this these LIs of x have the following form. Okay, so they're the product of a bunch of polynomials. So they go from j equals to 1 to s, where j is not equal to I. Okay, so I'm omitting the j equals I term. It's like in this product. And then I have x minus cj over ci minus cj. Okay, so each of these terms, of course, are just monomials. I'm multiplying s minus 1 of them, so I'm going to get a polynomial degree s minus 1 from this. So you might ask where this is coming from, and in particular, what are the defining properties of the Lagrange polynomials. Okay, so they're constructed in the following way. So these satisfy the following property, that if you were to evaluate the Lagrange polynomials at the quadrature points, so if you take Li and you evaluate it at the point Cj, all right, then the claim is that it satisfies what is called a Kronecker delta property. Okay, so it's the property that it is 1 if I is equal to j, and 0 if I is not equal to j. Okay, so in fact, you should think of this, if you will, as the defining property of the Lagrange polynomial. And it's easy to convince yourself that if you were to know that the Lagrange polynomial had this property and it was a polynomial of degree s minus 1, then you would immediately get a formula like this. And the way you see this, of course, is that if you look at when these things are 0, this Lagrange polynomial is going to be 0 at s minus 1 points. Okay, so you know that up to some constant multiple, this Li of x is going to be something which involves the product of x minus cj for j not equal to I. Okay, so it's going to be the product of these monomials, which each have roots at the point cj. And then the other condition, it's like, which you need to use is this normalization condition, which is that when you evaluate this polynomial at the point ci, that it normalizes to 1. Okay, so the way you interpret this expression for the Lagrange polynomials is that these x minus cj terms multiplied over j not equals to I are going to give you the condition that the Lagrange polynomial vanishes, has roots at the points cj, and then this term ci minus cj, 1 over ci minus cj term, is giving you the normalization condition, which is to say that when you happen to evaluate this at a point x is equal to ci, you get 1. Okay, so this is what motivates this. And then you can ask, well, if you have, it's like a polynomial, it's like which has this Kronecker delta type property, why is it guaranteed that you actually have an interpolating polynomial? So let's just see what happens when you do that. Okay, So now you have p of x is this linear combination from I equals 1 to s of g evaluated at ci, and then this Lagrange polynomial Li of x, right, where you have the property that Li Cj is equal to 1 if I is equal to j, and then 0 if I is not equal to j. Okay, so I'm going to evaluate this polynomial p at some one of these quadrature points, Cj. Okay, so this is equal to the sum from I equals 1 to s of g at ci, and then Li Cj. Right, that's just by definition. But this Li at Cj term satisfies this Kronecker delta property, so it's only 1 if I is equal to j. Okay, so this sum here basically collapses to a single non-zero term, which is when I is equal to j. Okay, so this is going to be g at Cj, because all the other terms are going to be multiplied into 0. Okay, so this is telling you that when you take the polynomial and evaluate it at this quadrature point Cj, that it recovers the original data at that point. So this tells you that this polynomial, which I've constructed out of Lagrange polynomials which satisfy the Kronecker delta property, right? This has the interpolation property that when you evaluate this polynomial at the point Cj, you get the original function value at that point. Okay, so this implies that p of x of that form is an interpolating polynomial. Okay, which is what you would like. Okay, so once you have the interpolating polynomial, it's like what we said was that you take this integral of g of x dx. Let's assume that's an integral from 0 to 1, and then I've approximated it by replacing this integral of g of x by p of x. Okay. All right, where p of x is this interpolating polynomial which I've constructed before. So let's see what happens. Okay, and we know that this is equal to the integral from 0 to 1 of this expression. So it's the sum from I equals 1 to s of g ci. It's like Li of x dx. Okay, so I can swap the integral and the sum. So let's go ahead and do that. So the sum from I equals 1 to s, and then this g of ci is just a constant with respect to x, so I can take that out. So I have g ci integral from 0 to 1 of Li of x dx. Okay, and so this term here, the integral from 0 to 1 of Li of x dx, is just something which you can pre-compute, okay, given what you know about the ci's. Okay, so let's just call that something. So let's just call that bi. And then what you have then is that this is equal to the sum I equals 1 to s of bi g ci. Okay. All right. So what this is saying is that you can approximate, that's like the integral of g by some weighted combination of the function values at the quadrature point ci. So these bi's are what are called quadrature weights. And then the ci are the quadrature points. Okay. All right. So now it's like we've solved the problem of what happens if you're trying to compute the integral over a reference interval from 0 to 1 in terms of these things. So as I said before, if you want to do the integral for an arbitrary interval, then there's some sort of rescaling, it's like trick, which you want to do. And so let's see what happens when you want to do that. Okay. So let's just recall what we have so far, that the integral from 0 to 1 of g of x dx, right, is approximated by some weighted linear combination, I equals 1 to s of bi times g at ci, right, where the bi's are given by the integral from 0 to 1 of the Lagrange polynomial Li of x dx. Okay. All right. So that's what we've done so far, and then what we would like to do then is to take this formula and then apply it to an arbitrary interval. Okay. So to approximate say the integral from t0 to t0 plus h of g of t dt. All right, so this is, of course, the relevant thing to do when you are trying to use numerical quadrature to approximate the fundamental theorem of calculus. Right, these are the kind of intervals you tend to want to work with. So what you do is you do a change of variables. Right, so you perform a change of variables. Okay, so you have t of x is equal to t0 plus h of x. Okay, then it's easy to convince yourself that if you allow x to go from 0 to 1, right, then this thing will go from, then t will go from t0 to t0 plus h. Okay. Okay, so then it's like, you know, if you look at it at the point of view of infinitesimals, this says that dt is equal to h times dx. All right. So so you can perform, it's like a change of variables formula. It's like to the integral. So you start from the integral from t0 to t0 plus h of some integrand g of t dt. All right, and I'm going to write this now as the integral from 0 to 1, but with respect to the variable h, the variable x. Okay, so this will be g of t0 plus hx, okay, h dx. Okay, so so once you have it in this sort of standard, it's like interval, then you can apply the quadrature rule we developed to approximate this. So this is approximately equal to h times the sum from I equals to 1 to s of bi, right? And then g evaluated at t0 plus hci. Okay. So that's how you take a standard method and apply it to an interval of arbitrary length. Okay, and the reason, of course, it's like to write it in this way is because when you compute these sort of quadrature weights, the bi's, right? So these things can be pre-computed ahead of time. They don't depend, it's like, on the time step h when you do this. Okay, so that's really the advantage of you know, referencing everything in respect to this uniform interval is that then the quadrature weights and the quadrature points are formally independent. It's like of the time step h, all right, and then you do the rescaling. It's like to tell you where you want to evaluate things. Okay, so as is the case with a numerical ODE method, it's like you can also talk about the order of accuracy of a quadrature rule, right? So order of the quadrature rule. Okay. So it's, as is mostly the case, it's like when you look at order of accuracy, we're talking about some asymptotics as the time step h goes to 0. So if you look at h going to 0, right, then if the the numerical quadrature approximates the exact integral to big O of h to the p plus 1, right? Then we say that p is the order of the quadrature rule. All right, so we've talked about what are particular called Newton-Cotes methods, where you've constructed the quadrature weights from the quadrature points. Okay, and so you can ask, well, is there something which can be said about the order of accuracy? It's like one of these quadrature rules which are obtained in this way. So the point is that any quadrature rule that is based on sort of an S-point interpolation has an order of accuracy P which is greater than or equal to S. Okay, so you might ask, well, how, it's like how you guaranteed it's like to construct sort of a good method. Okay, so you're guaranteed at least it's like an order accuracy which is related to the number of points you use in the interpolation. But we haven't said how you go about choosing those quadrature points. So the basic upshot is that if you choose the quadrature points sort of wisely, okay, then sort of higher order than S can be achieved, right? And as we'll see, it's like as the quarter progresses, this is going to be related to something having to do with orthogonal polynomials. So this choice of quadrature points to achieve sort of higher order than S, right, is related to the theory of orthogonal polynomials. Okay. So let's just stop here for now.